So now I'm going to discuss some different forces or phenomenon which end up determining the final temperature. So the heat generation, as I mentioned, it's equal to the strain squared. And so the heat generation has a distribution which is proportional to cosine squared and cosine squared formulation. And for here I just had a arbitrary constant determining this height, which is related to the quality factor, which I'm going to be showing. And the heat dissipation, you know, because conduction occurs, if heat is generated here, it's going to want to flush out and even out. So because the heat wants to be even, it's going to sort of transfer itself to the edges of the ceramic over time, a small amount of time, through heat diffusion, heat conduction. So as the temperature of the edges increases, also heat loss will increase. Heat loss according to convection is proportional between the temperature of the material or the transducer and the outside temperature. In this problem, what I basically did, I used this heat generation equation, and I experimented with different amounts of heat generation, which would get me to the experimental temperature distribution. So I played with the heat generation. I measured the heat loss by doing an experiment where I let the ceramic cool, and I see how long it took to cool, and I measured the heat HD from that. I measured the heat generation coefficient. I knew the distribution, but I had to get HG, and I got HG by changing it and trying to experiment at which level of HG would match the experiment. So here's basically what I did. I had the temperature distribution. You see I'm holding the sample at the middle, and because I'm holding the middle, there's sort of this hump there, experimental error, sorry. Then I use the heat transfer model, and I get the HG parameter, and then I use this parameter. I use this function, which I derived from energy relationships. So as you notice here, here's the stored energy, here's the lost sort of energy relation, and this something's canceled out, and this beautiful relationship end up coming out. So here's a small experiment which I did, small or published, I guess. So this is a while ago, so we've improved our abilities here at our lab, but we are comparing the 3dB method and the temperature analysis method, which I'm calling the temperature analysis method, to determine the mechanical quality factor. The operation is at resonance. We're using a constant vibration velocity drive. So throughout the entire measurement, at each frequency, we're using a constant vibration velocity, which constitutes as high power. You saw the 16 degrees temperature rise. The material is a hard PZT. We're talking about longitudinal vibration. And the experiments were repeated 5 times to determine the standard deviation. So here's an experimental setup. We're driving the ceramic using a function generator and power amplifier, controlled by PC. The measurements are occurring from a current probe, oscilloscope voltage probe, measuring the vibration from a laser Doppler vibrometer aimed at the edge. Although we're only measuring the vibration at one point, we can estimate, and pretty much we can calculate the rest of the vibration, because we know it occurs in a sinusoidal fashion. And the edge vibration tells us the magnitude. Okay, so when we get the temperature from the temperature signal, which I'll be explaining soon, how to measure temperature on a ceramic. From a temperature thermal camera. So basically, here's what happened. I measured the quality factor at different frequencies. Here's the resonance frequency at 20.05 kilohertz, and I measured the quality factor. So as we are getting closer to the resonance frequency, we're seeing that the quality factor is decreasing. And hey, if you measure during the 3D method, we get a quality factor of about 507. So perhaps we can estimate that this would agree. For this set of experiments, I wasn't able to measure the temperature exactly at the resonance frequency due to some technical difficulties. But technically, we could have done it, but for practical reasons, it wasn't performed. So in this study, we had a larger deviation for the 3dB method, but you know, they had a standard deviation of 15%. But I think now we're better than that. I think we can say, depending on what kind of vibration testing you're doing, you can probably get within 5%, depending on your range. So as we saw, this has a very low standard deviation. It sort of depends on your measurement method. So I measured the temperature distribution. Okay, measure the temperature distribution, and we fit that to using the Hg parameter to the experimental temperature rise. So what we just discussed was some important factors, some important things regarding temperature. How loss occurs in the material is due to changes in energy, and it has to do with frequency, because the more cycles you have, the more power you dissipate. That's one thing we talked about. It matters about how much energy you're storing, because if you're storing more energy, you're technically losing more energy, because the energy loss is proportional to the energy stored. So we have that stored energy term, and we have this power dissipated. So if you can kind of look at this formula, this top part, it's sort of like the mechanical power, if you want to say, but although it's not mechanical power, because power is not, because the energy is just going from up and down, it's not really being transferred. So to call it power, it's not really power, but it ends up sort of looking like that, and the units match. So the quality factors, of course, it has no units, or it has so it has no units. The quality factor for the K through 1 material only is equal to the tangent phi 1 prime, which is also equal to the tangent phi for low values, which is also equal to the S11 double prime divided by, so S11 prime divided by S11 E double prime. And in this case, for the tangent delta, no, sorry, this is over 1, this is over 1. This would be see, so this is sort of backward than we normally think about it, because the compliance is sort of 1 over the spring constant, sort of constitutes of the Young's modulus, and Young's modulus is usually what we think about to measure energy, and that's more natural. But actually, if you want to talk about inputs and outputs, compliance has to be an input, because you apply stress, you don't apply strain. So this is stress and this is strain. As if I didn't explain it, I just did. So therefore, it's sort of backward here. I probably explained that earlier, but just note that there's a subtlety in which one of these goes on top. Does S double prime, which is the imaginary part, go on top, or S prime goes on top? Actually, S double prime is larger than S prime, but that's just because we sort of use this inverse sort of relationship, which we're not normally used to, because we're normally used to using compliance, using elastic modulus before we came to piezoelectric studies. So I want to thank you for listening to my research and work. I look forward to hearing from any comments, as people have been sending them over time, sending thank you. I also thank you for watching, and I hope you learned a thing or two, or more than 2 things, hopefully. Thanks for watching.